All right, two really critical measurements that we're going to talk about today. Measurements you're definitely going to see May 10th, and it also goes a long way in helping us understand how well a line would fit a set of points. One of them is called the coefficient of determination, and one of them is called the standard error. Now here's what I asked you guys to do. I just asked you guys to find all of these things called residuals, square those values, and add them up. So graphically, what am I talking about here? How far is it from this point to this line? I think yesterday we talked about this, and it was actually something like 12 away. Negative 12 was the actual distance. Look, somebody actually studied for 126 minutes and got a 79. I would hope that if you asked me how many minutes you were going to study and it was 126, I'd give you the answer 79 because that's real. But unfortunately, the line doesn't have an opportunity to go through every single one of those points. So when you ask me and I stick it into the equation that's trying to predict the future, it's not going to necessarily have the exact right answer. So what we're analyzing is how far away is my prediction from the right answer? Okay, we call that an error. Okay, another name for it is a residual. So what all of you have just figured out for me are all of these residuals. I wish there was no red at all. If there was no red at all, my line would be exactly perfect in predicting the future. Okay, so red is kind of bad here. I wish we didn't have any of this. One of the things we're going to figure out today is, typically how much red is there? Like, in other words, if you tell me you studied for 40 minutes and I give you an answer, wouldn't it be kind of nice to know, hey, I'm usually off by about 4 points or 6 points? Okay, that's going to be something we're going to talk about today. All right, so I ask you to find all of those. Now, those of you who are still struggling with this, here we go. Okay, the first thing that you have to do is you have to go into your calculations and in your calculator's memory, put the equation of that best fitting line. Now your calculator has it in the memory. If you don't do that, you can't follow these steps. All right, what is a residual? This is the fancy formula for it. We take the actual values. These are the real test grades. This is real. And we want to subtract what our predictor line would tell us should be the test grade. So put that in our calculator. We'll go to the editor. You've got to highlight the top or you're going to get one of those mismatch errors. Be careful of that. So I want to take the actual test scores, that's L2, minus, now don't forget the parentheses, okay, or you won't distribute the minus, and now let's paste that equation right in here. Do that, you go to VARs, down to statistics, over to equation, there's your equation with all the significant digits. Now it wants to know, hey, where are the minutes studied at that I'm plugging into this equation? Okay, you just go right over the X, put L1, close off your parentheses, and there are all of the errors. Look, if you tell me 45 minutes, you want to know the answer? The answer I give you is going to be 12 off. 12 away from the reality. That's a residual. Now, just to kind of preload what's going to happen later, what would happen if I took the average of these numbers? In other words, if I was trying to find the average error, what would I get if I took the average of these numbers? 0, right? No, they add up to 0, so we're going to have to deal with that later. Okay, so what I asked you to do was then to square all these and add them up. I got a little fancy shortcut for you. If you'd have just done right now a 1 var stat on L3, those are where my residuals are, right? Does anybody see your number on there? That's one of the things it does for you. It squares them and adds them up. That's one of the calculations it does for you, and that's the reason for it. Now, I'm sure most of you just squared them and put them in L4 and added those up. That's fine. Okay. So I know, and I got an abbreviation for you now. This is sum of the squared residuals. Minitab uses this abbreviation, SSE, sum of the squared errors. You might also see this as SS resid. So if you see either one of those abbreviations, it means you've taken your residuals, you've squared them, and you've added them up. So we got, for this problem, 1,258.02. Now, I'll take volunteers on this one. This took like 10 minutes back in third period. What is significant about that number? You need an overall understanding of what we're doing here. What is significant about that number? Thank you. What?
Well, since that you were able to add them all up and then have it not be 0, this way you can actually put a number to your error.
The significance of it, though, yeah, that is a number to the error, but what's a big deal about that?
If y hat is the least squared regression line,
Which we know it is.
then you put it in there, and that'll be the least possible number.
You got it. Say it another way. If I like what he said. Anybody? He said that would be the least. What is he saying? Can you say it another way? You say it another way. Yeah.
Okay, so you're finding the residuals, and so you're dealing with the residuals. So since it's the least squared regression line, that number that we came up with is the least possible number that we can come up with.
You got it. Let me just say one. Let me just add one thing to it. I don't care what other line you pick. Try another line. What number are you going to get? Are you going to get a number bigger than that or smaller than that? I got to have 35 people knowing the right answer to this. If you'd have picked any other line than this one, pick this line. What do you know if you went through that same process and took all the errors and squared them and added up? Would you get a bigger number or a lower number?
Bigger.
Bigger. That's right. That's why that one won. That's why this was the best one. It had the least red. Red squared added up. It had the least. It was the best predictor of these test scores. I need your basic understanding of why that line was picked. 12,058, that was the best line. You pick any other line in the world, do that process, you're going to get a number bigger than 1258. Yeah?
So are we just squaring this to take out negatives?
Yeah, remember if I just found the sum of them, it would add up to 0, so that's why we're squaring. Okay. All right, good. Well, all right, this coefficient of determination. Let's play this game. What was the, anybody remember what the average test score was? The mean test score, what was it? It's in your notes somewhere. It was 50-something. What's the average test score here for these 10 students? 59.7. What if I'd have done this? Here's the deal. Hey, I got this great deal. You tell me your minutes studied, I'm going to predict your test grade. How many minutes are you going to study for the next test, Jane?
126.
126 minutes. I think you're going to get a 59.7. How many minutes are you going to study for the next test? 30 minutes. You're going to get a 59.7. How many minutes are you going to study? 6 minutes. 59.7. Okay. What am I doing? I'm just taking the average. That's not a horrible guess, right? I'm giving the person, hey, I'm giving you an idea. It was the average on the test. Okay. But is that taking into consideration how many minutes you study? No. So here's what we're going to try to figure out. We're going to try to figure out is, tell me how much better it was for me to go through all that work and create the line. Is it better? Did I eliminate some of the problems, some of the errors? Or is it that guess just as good as your line? That's what this thing called coefficient of determination is going to find for you. Gives me a percentage of how much better it was to work my line than to just always guess the average. All right, here's what I mean by that. Let me show you this. Instead of the least squared regression line in here, I'm going to put the mean. It was 59.7. I just learned this morning. It's great. I can actually do the mean calculation right here. List. I go to mean. Now this is not something you're going to have to do. Okay, so you don't have to follow along. I just kind of want you to see what I'm doing and follow along. Kind of conceptually understand what I'm doing. This is always guessing 59.7. How many minutes you study? I studied 30. 59.7. Okay, so that's the line that's always guessing 59.7. Well, let's find out how far off that line is. And I'll do that in black. So right here, that distance is how far off that reality was from just guessing the mean. So which is better on this one, the red or the black, the regression line or the mean line? Yeah, looks like regression did a little better, right? Okay, I'll do that on all of these now. So that one, the mean line gives you that kind of an error. That kind of an error. That much of an error. Actually, the mean line did better here, didn't it? Than our least squared regression line. Did a lot better here. Not so much here. Not so much here. Okay, take a step back now. If you could just compare the red and the blue. The red is our regression errors. The black is the errors I got from just giving you the mean every time. Is it worth our while to create a line for those points or just give the mean? Which is better, do you think? The regression line. Aren't the red lines as a whole probably smaller than what I've got for the black lines? I agree. How much better? I want to put that in green. Well, I don't know how much better there, but I can easily do it here. Wasn't it that much better? Mm-hmm. If I take the mean error and I subtract what I got as an error, that tells me how much better I got. So I got some green going on here. Not there. Not there. I got green here. A lot of green here. Green here. There should be some green here, but I could do subtraction. Okay, yeah, there's some improvement there. You know what? Drawing my regression line took away a lot of my problems. Okay. All right, let me go figure out how long those black lines were. You don't have to do this, but let me just show you how we would do it if I went into my calculator. I'm going to figure out what the errors were like for those black lines. So I'm going to do the same thing. The actual values minus, and then just the mean of the L2s. Second list, math, mean of the L2s. Yeah, let's do it better, right? That was the black line. This was the red line. It was about 3 better. That's how long the green would have been on that one. So I'm doing a little bit better. Okay, this has a fancy name as well. Okay, it's called SST, sum of the squared total. Okay, so if I did a 1-bar stat on that guy, the sum of the squared total would be about 2,634. So that's what the black line squared added up to. The red line squared added up to 1258. So what was the difference? Let's give me an idea of green. Okay, green, I would just subtract those two. So SST minus SSE, that's going to give me the green. Give me a number. 2634 minus 1258. 1,376. Can I say this another way? By making that least squared regression line, didn't we get rid of, didn't it help me out on 1,376 squared error points? It's squared, right? So, but didn't it help me out? Yeah, it helped me out. That's what the coefficient of determination is. Now, I'm not going to make you do all this craziness, okay? I'm not even going to make you memorize this formula. This is the formula for r squared. But what I need you to do is understand this verbiage as it relates to what we did today, the green stuff. Now let me read this sentence off to you, and let's see if that sentence makes a little more sense now. You have to say it this way. So let's actually figure this out. So I want to find out the percentage that went away. So that's how much went away over the grand total. That's how much total error there was, and this is how much went away. So somebody throw that fraction in. It's going to be 1376 over 2,634. What is that? Point? About 52%. So here we go. That's what r squared is. Let's follow this sentence and see if it makes sense now. 52% of the variation. Now, why do they use the word variation? Remember variance? It wasn't variance, the standard deviation squared, so it's the squared values. So that's why they're using the word variation. Aren't these all squared errors? Remember, we couldn't just add them up because they'd add up to 0, so that's why we had to square them. So can we say that 52% of the variation is explained by the least squared regression line? Hey, when I drew that line, 52% of the errors went away. That's green. That's the green stuff. 52% of the total. So green is like 52% of the black. So 52% of the variation is explained by the least squared regression line. Then I put these words in, which you're going to have to do. Of the least squared regression line, predicting test scores based on minute study. Poof! I wasn't lazy. I just didn't give you the average. I took the time to create a line. 52% of the bad stuff went away. My least squared regression line explained away 52% of the bad stuff. I'd like 100% of it to go away, actually, but this is. All right, maybe some of you have already thought about this. Is there an easier way to calculate r squared than to have to go through this formula? What do you think? No, not just the calculator. You think there's an easier way? I mean, that's the easiest way, I agree. But you think there's another way to calculate r squared? How about squaring r? What was r in this problem? 0.7227? Square that. See what you get. You get around 52%? Yeah. R squared is just the correlation squared. Now, step back a second. R! Didn't we do like z-scores and multiplied them together and added them up and we got this R thing? And this is all about error analysis? So I don't know how that worked, but it does work. The coefficient of determination is just the correlation squared. So if you know R, you can easily calculate R squared. But what I need you to understand is what it represents. It's the percent of the variation that got explained. Okay? The bad stuff went away. What percent of the bad stuff went away? Okay? Yeah.
So for that sentence, percent of variation, for the last part where you put minute study, is it always going to be the explanatory variable?
Yes, so we're trying to predict the response variable based on the explanatory variable. And whatever those are in your problem, then you would put those words in. Yeah?
This is always off the mean? Off the...
Yes. It's how much did taking the time to fit a line to these points, how much better did it do than me just being lazy and giving you the average test score? Okay. All right, the second really important statistic that we're going to learn today is called the standard error. Now, you guys told me that I cannot just take these residuals and find the average of them, can I? Why not? It's going to be 0. So we're going to do the same thing we did for standard deviation. Remember all the deviations added up to 0, and then we squared them and added them up? Okay, that's exactly what we're going to do here. Now this is a formula you need to memorize. This is not on your green sheets, and this is something that you are going to be, next test and on May 10th providing to answer the question. Okay? We take the sum of the squared errors, which is what we did for the warm-up. You take all the residuals, you square them and add them up. And then remember when we were doing degrees of freedom for one variable statistics, we subtracted 1. Well, now we have bivariate data, so they actually want us to subtract 2 here. Since there's 2 sets of numbers. Okay? Again, don't really completely understand it, but that's just how they want us to do this on degrees of freedom, because this was a sample. But I'll explain a little more about that later. So that's the formula we're going to want to use, but I need you to understand what it means. Hey, what is this on average? What am I looking at being off by? So let's go ahead and do that. So the standard error for this problem, now remember you're always going to write down the formula. So it's the square root of the sum of the squared errors, or SS resid. Sometimes you'll see it like that. And we're going to divide that by n minus 2. So in this problem, the sum of the squared errors, you guys told me was 1,258.02. What are we going to divide by in this problem? We're going to divide by 8, right? There's 10 points, right? Somebody throw that in your calculator and tell me what the standard error is for this set of numbers. Now how I want you to think about this is critical. I need you to get this. These guys, typical number's about 12, 12 and a half. What does that mean? I mean, an honest person would say, hey, I got this new great thing, it's awesome. You give me your minute study, I'm going to tell you what your test score is going to be. You're all fired up. Yeah. So you tell me I'm going to study for 30 minutes. Do these calculations, you're going to get a 72. Okay, just so you know, I'm usually wrong by about that much. On average, that's how much I'm usually wrong by. Isn't that good information to know? I mean, you know, sometimes I might be wrong by less. Sometimes I'm wrong by more. On average, I'm off by about 12 and a half. And that's the standard error. Okay? And that is a formula you need to remember, and that's a formula you have to do. Minitab output. I showed you that the other day. Go find that Minitab output. These numbers are on there. The Minitab was on page 156. Go find SSE. Go find SST. And actually the green is on there as well. Remember, we're looking at the top, Minitab output. Does everybody see towards the bottom there? Where you see what do you see? SS. There's your sum of the squared. And on the left-hand side, you see error. So it was 1.61. There wasn't a whole lot of errors on that, was there? Compared to ours, anyway. SST, the total, that's the black. And actually, regression up there, that's the subtraction of the two. That's the green. So I guess theoretically they could give you a Minitab output, and you could be responsible to get R squared that way. I've never seen that question given, but it's potential. If you guys remember, oh yeah, it's how much got cleaned up over the total. Okay, that will calculate R squared for you.
Is that why on presidential polls they usually have the plus or minus 3? Or is
Right, we're going to talk about that a lot. You know, it's unfortunate. We get into why there's a plus or minus 3 and why they do it, but we have to be elections. So we're going to talk all about that, but yeah, we'll figure it. You'll learn all about that. Okay. All right, now, some things you got to keep in mind about this least squared regression line. Obviously, these are multiple choice questions waiting to happen right here. Number one, if you switch the explanatory and response, well, let's start here first of all. If I switch the explanatory and response, so I made this L1 and L2. So in other words, I'm using test score to predict how many minutes you study. What will happen to R? What will happen to the correlation? Think! What will happen to the... You've already been asked this question before. What will happen to R? What will happen to the correlation if you switch the explanatory and response? Yeah. It stays exactly the same. Remember, didn't we calculate it from z-scores? And remember, 3 times 2, 2 times 3, if I switch around the z-scores, don't I still get the same number? Remember that? So R is not affected at all. However, if you switch the x's and y's around, if you switch the explanatory and response around, you have got to go calculate a new line. In other words, you can't do this. What was the equation for this? It was like test score is equal, it was like 48 plus like 0.33 minute study. Wasn't that kind of the equation for this? So here's what you'd be tempted to do. You're saying, okay, you come in the next day, okay, smart guy, I'm going to tell you how my test grade, you tell me how many minutes I studied. So you'd say, oh, I'd say, okay. So you say, okay, I got a 75, predict how many minutes I studied. Don't plug that in there and solve for this. Isn't that what I've been telling you to do on z-scores? Just plug them in where you want and solve for them? You can't do that here. And here's why. Think about this. We created a predictor line that tried to minimize the errors from this, right? Isn't that those vertical lines? If I'm now trying to minimize the errors on minutes studied, okay, I want to do the horizontal differences to minimize those errors. So the point of it is, and you have a problem like this tonight, if they give you, you know, they say they're giving you the response trying to get you to do this, don't use that old equation. Just do a linear regression L2, L1. It's going to give you the same R, but you're going to get a different equation for the line. Use that one. Okay? All right, number 2, the book makes mention, hey, just understand, there's a relationship. Remember this equation was how we found slope? It's in your green sheets. There's a relationship between the slope and correlation. One of the biggest things that you should realize is they're going to be the same sign. Right? If r is positive, wouldn't you get a positive slope out of your line? Yeah, that makes sense, right? The points are going up this way. If r is negative, the slope will be negative. That slope of the line you get will be negative. Okay? There's a few other similarities to think about, but just for right now, just remember, they're going to be the same sign. This one you should already know. Right? The mean of the x's and the mean of the y is always going to be on that least squared regression line. And then finally the last one. R, now remember R, even though we can calculate them totally different ways, but you can just square one of them and get the other. You think they mean the same thing. They give you totally different information. R tells you how strong, remember weak, moderate, strong, how good the line is, and the direction, positive or negative. Whereas R squared tells you the percent of the bad stuff that went away. What percent of the bad stuff went away when I stopped just giving you the mean and I started plotting the points comparing the minutes studied off the least squared regression line? Question. If I give you R, can you calculate R squared? So if I give you the R value, could you then tell me R squared? I'm getting a lot of nods. Okay, I'll buy that. If I give you R squared, coefficient of determination, can you get me R? Yeah. Be saying no. You think it's a trick question, don't you?
It is no.
It is no. It is a trick question.
Yeah, there's negative or positive R.
Very good. Did you hear what he said? Let's say I give you an R squared of 64%, 0.64. And I say, okay, go get me correlation. No problem. Can you take the square root of 0.64? It's 0.8. But do you know whether that's a positive 0.8 or a negative 0.8? Not sure, right? So the answer could either be either. So just if I give you R squared, understand that the R value could be positive or negative. It depends on how those points lined up. Okay? Okay, a lot of stuff today. I think this is the last new stuff from the chapter. We're going to spend a couple of days reviewing, but you've got now a ton. 2 things we learned about today. This thing called coefficient of determination. I want you in the back of your mind to have that green knowledge there to call on, to have a general understanding. Why? Because I want you to be able to understand this. This is a sentence you got to know. You'll see that sentence on your AP test May 10th, and you've got to know that's R squared, but I hope you actually know where it came from. And then, this is a biggie, standard error. That gives me an idea, hey, I'm going to use this line, but I'm usually off by about this much. Okay?